Good morning, ladies and gentlemen. Welcome at CWI in Business, live from Amsterdam, here in the harbor. No, this isn't a green screen, this is real. From the studio, we're going to talk about multi-party computation. My first guest here on the table, I will briefly introduce. Here we have Lisa Kool and Ronald Kramer, both from the cryptology group of CWI, and Thijs Veugen from TNO. More on them later, but first, CWI in Business. This is actually already the 23rd edition, and they do it every 2 years. So this dates back from, well, let's say half a century ago. But for the first time, virtual, of course. And if you look this back afterwards, well, today is the 13th of September. We also have virtual with us Marcel Keller, all the way from Australia. Marcel, say hi to the folks at home. Yeah.
Hello.
Hello, Marcel. What time is it over there?
It's just 6 o'clock here, or already, if you will.
Okay, 6 o'clock at night. Well, here it's 10 o'clock in the morning, but we can hear you, and there's no latency, fortunately. We'll be seeing you later on your presentation. So, CWI, the Institutes for Mathematics and Computer Sciences, organize this event every 2 years to present itself together with its business partners. So last edition was 2019. And this year our business partner is TNO, the Dutch Organization for Applied Science. And well, actually CWI and TNO collaborate on many cryptology topics, like post-quantum crypto. Perhaps you saw this webinar a couple of months ago. But today will be on multi-party computation. And let's first test your knowledge, whether you know, well, anything about it. So the first poll question will be, how familiar are you with secure multi-party computation? Yeah, is it on screen? It is, yes. So it could be that you never heard of it. Well, that's why you joined this webinar, of course, to learn about it. Could also be that you are a newbie, or you have worked with it, or you're an expert. Well, perhaps you are. Well, for the people who never heard of it, let me briefly summarize what Wikipedia says about it. So, multi-party computation methods for parties to jointly compute a function over their inputs while keeping those inputs private. Normally with cryptology, it's to protect the data from adversaries. This is to protect the data from each other, collaborating on it. So let me see the poll. We see 2 people who never heard of it. Well, welcome. Yeah, you're going to learn a lot. 16 of them are a newbie, that's 40%. 33% have worked with it, might be colleagues. Oh, and we have 23% are experts. Well, for all of you, please join us also in the chat. If I throw away the poll now, hide this. Yes. Now you can see the chat again, and we have 2 chat moderators sitting now at home, Arend Baarsen and Sergej Ver. They might also answer your questions or select the questions, which I can see here on the screen. So thank you very much for that. Going back to the program. Yeah, excellent. Okay. We'll kick off with the first part, which is more on the fundamentals of multi-party computation. So we're all on the basic, similar level of understanding. And in the second part, after the break, we'll go into the case studies of application of multi-party computation. But we'll kick off with an introduction by Lisa and Ronald. So here on my left, Lisa Kool, she's a researcher at the CWI cryptology group since October and part of senior staff. But she already worked here in 2015 when she finished her master thesis. In the meantime, she got her PhD at Karlsruhe Institute of Technology and worked as a postdoctoral researcher at Technion. Next to her, Ronald Kramer will kick off, and he is the head and founder of CWI Cryptology Group and professor of mathematics at Leiden University. He's also a member of the Royal Netherlands Academy of Arts and Sciences and fellow of the International Association of Cryptological Research. Perhaps he's best known for his work on hash-proof systems and encryption with chosen ciphertext security, known as Kramer-Shoup encryption, which is also an ISO standard. And for his work on cryptographic protocol theory, and of course, his work on secure multi-party computation, and that's why he's here. So let's kick off with Ronald Kramer.
Thank you, Chris. So in this introductory talk that Lisa and I will be presenting, we're going to give some basic ideas from secure multi-party computation. So it's divided in two parts. Part one is what is secure multi-party computation? That's the part that I'll be presenting. And part two is how does it work, roughly speaking? And that's the part that Lisa will be presenting. So let's first discuss a little bit what is secure multi-party computation. And the first thing I'll tell you is, how to contrast that with classical cryptography in a sense. Is secure multi-party computation just an application of classical cryptography? Now, classical cryptographic tasks all pertain to secure communication. This means data confidentiality, which is something we solve with encryption or public key encryption, data authenticity, one can use message authenticity codes to solve that, or non-repudiation, which is solved using digital signatures. To show to a third party that somebody said something, you can really prove that. So the digital equivalent of a handwritten signature, if you will. So all these properties are part of the realm of unilateral security, which means protecting the good guys from the bad guys. So here, the people who operate the system are inside, and there may be bad guys on the outside, and the cryptography is to protect the ones on the inside from the bad guys on the outside. Now, this is to be contrasted in a very strong sense with what I would call multilateral security. The first part is unilateral security. So multilateral security is all about secure and private processing on mutually private data. So you have a bunch of parties. Each of them may have their private data that they don't want to share with the others. And somehow they still want to process on the entirety of it. And they want to process with the purpose of enabling some controlled release of information, some function on the joint set of mutually private data sets. And they want to do that in the face of mutual mistrust or conflicting interest. They may trust each other to some extent, but maybe they have different business interest or whatever. And also, they want to do that in the absence of a trusted party, a trusted third party, a trusted arbiter. So this area is fundamentally different from unilateral security. This notion already makes sense in a world of two, whereas secure communication, unilateral security, doesn't make any sense in a world with two, because there wouldn't be a third, an eavesdropper. So there you already go, it's something completely different. Now, technically, to resolve this sort of problems, and I'll give you some examples in a minute, requires dedicated cryptographic primitives, not just encryptions or signatures. So for instance, an example that I'll be mentioning is like secure auctions, where people have private bids, and somehow the result of the auction should become known without revealing the bids. Now, just encrypting your bids won't help you. It doesn't help to dig a hole in the ground, stick your bid in it, and close the hole. How are you going to compute on that? So it should be clear it requires some special primitives. So let us go to some toy examples. A simple toy example is two-party dating. So the goal is you have two parties, X and Y, and they want to jointly determine whether there's possibly some mutual attraction. And each of X and Y should learn the outcome, whether it's true that there's mutual attraction, or no, when there's none, no such thing. When you study this problem, you see it's already unavoidable that under the conditions that I've just given, that if there's a fancying party, then that party is going to infer the position, the other's position from the outcome. That's easy to see. And you also see that a non-fancying party knows the outcome in advance, because there will be no. So what is left to be solved, and that's the goal here, is phase saving. So if you're a non-fancying party, then you would like to ensure that that party remains ignorant about the other's position. So that saves the face of the party who's fancying, yeah? And if the other is non-fancying, then that other party is not going to learn that you were fancying. So that's excellent for 1990s dating shows. They don't do that on television anymore these days, I believe. Now, historical toy example from 1982 is the millionaire's problem. Two millionaires want to figure out who's richest of the two, but they do not want to reveal to each other by how much. Another simple example is voting or elections, where you want to have the tally be revealed, the outcome of the election, but individual votes should be kept secret. And auctions, there we go. You know, auctions, there's many different types of auctions, simple auctions, more complicated auctions, but just picture a very simple one for the purposes of this introduction. You know, highest bidder wins, so to speak. You just want to reveal the winner, but you might want to keep the bids of the other parties secret, even from the auctioneer. You know, maybe this auctioneer could be doing front running with it. So there's an incentive to use secure multi-party computation in this setting. Then we have benchmarking. So across an industry, they might like to determine best practice, but without revealing their trade secrets to their competitors. So for instance, companies would like to jointly compute the average of the salaries of managers or other statistics about their production process, but they do not want to reveal anything else to each other in the process. Now, another example, a bit more technical from cryptography, is zero-knowledge proofs. It's a special case of secure computation. You have a theorem on the table. I have a proof of this theorem, complicated theorem, behind my back, and I want to convince you that the theorem is true, but without giving you the proof. So somehow I should be able to convince you, a skeptical verifier, without actually handing the proof to you for you to verify in detail. So somehow we should do some tricks there. Now, so let's go into a bit more generality here. This is maybe a bit technical slide for some, but on some higher level secure multi-party computation, if there are n parties, you have some sort of a function. That could be the function that determines the outcome of an election given the votes. But here it's an arbitrary function that you can choose in a number of variables, x1 up to xn. Each of these variables can take some value from a finite set. The variable xi corresponds to the ith party. So this ith party wants to keep the input secret. And the function is just some value in a finite set 2. Now, there's these n parties, p1 up to pn. Each party has a private input xi in this finite set. And now you could somehow say that the problem of secure multi-party computation for this particular function is how can they jointly correctly compute the outcome, the function f applied to the respective inputs x1 up to xn, that's the value y, without revealing anything else about their respective private inputs, except what others may infer from the outcome and their own inputs. Now, in the dating example, that function would be the f of x1, x2, with x1 and x2 a binary value, 0 if you fancy the other, do not fancy the other, and 1 if you do fancy the other, and it's just the AND of these two bits, which I have just written as a multiplication in f2. Okay, so, but a more enlightening and workable view, perhaps, and this is maybe the idea that you should remember if you didn't already know it, is you might think of multi-party computation as in the following way. So how can parties jointly, without external help, emulate the following thought experiment? So to emulate a virtual incorruptible mediator that I call omega, who would solve it for them? So the situation is there's omega in the sky, or on top of a mountain, or whatever you want to picture, and each of the end parties has a private channel with omega and sort of can transmit the secret input of that party to omega. Now omega is trusted and incorruptible. Omega receives all the inputs and then computes the function value and returns it, maybe by megaphone, to the parties, and that's the end of it. So that is the solution with the trusted incorruptible mediator. Now, secure multi-party computation is all about emulating exactly that functionality, but without requiring access to omega. So the parties should jointly simulate by cryptography, by dedicated cryptography, the functionality of this precise omega. I conclude my part by just, it's fairly technical, but what would this mean for zero knowledge? So you have a theorem and you have a secret proof. So one party has as input the secret proof, the other party has no input. The prover who has the proof privately submits the proof to omega, omega checks it. omega announces to the verifier whether the proof is valid, and now you see that if the prover would be lying, omega would he would be figured out by omega, and the verifier doesn't get any more information about the proof. So zero knowledge proofs is really about how can the prover and verifier jointly simulate omega so that two properties hold. A misbehaving prover cannot lead the verifier to accept the false theorem. And second, a misbehaving verifier remains ignorant about the proof. So I guess this concludes my brief introduction about what is secure multi-party computation. I'll give the floor to Lisa, who is going to talk about how does this work.
Okay, so thank you very much, Chris, for the introduction, and thank you, Ronald, for handing over. So yes, so I hope all of you, every one of you now has an idea what secure multi-party computation is. So what is left to answer is how does it work? And let's go a bit back in time and see the start of secure multi-party computation in the 80s. So in 1982, Yao gave a general solution for two-party computation for the two-party case. So if you think about the toy examples, the millionaire's problem, the dating problem, but more generally any secure two-party computation that you can think of, any problem that you can wish to compute, with the downside, or with still like a caveat, that it assumes that the parties honestly follow the protocol instructions. And then in 1985, Goldwasser, Micali, and Rakoff gave the solution to what was just presented by Ronald, namely zero-knowledge proofs for all of NP, meaning that every theorem that has a proof, that if you see the proof, you can efficiently be convinced that it's true, the prover can actually convince the verifier without having to reveal the proof, and also without having the omega in the sky, just by interacting with the verifier. And then a landmark result was the theorem by Ben-Or, Goldwasser, and Victorson, and also Schaum-Crepot and Daumgart in 1988. And note here that with David Schaum, the CWI was already part of the birth of secure computation, so to say. And basically what the theorem states that if you assume that less than 1/3 of the parties corrupt maliciously, so you have 2/3 of the party acting in an honest, non-malicious way, then you can actually simulate this virtual incorruptible mediator omega, so you can get secure computation without the need for a trusted third party. And so how does it work? What do you need? How do you get there? And what we need for that is to understand, like, first effect, namely that any function f that you wish to compute can be given as an algorithmic network of additions and multiplications, so-called arithmetic circuit. So all we have to figure out is how can we do additions and multiplications. And then the very basic primitive that we use here is a dedicated encryption scheme. And you can think of this encryption scheme like you think of it as a puzzle. So to encrypt a value, you split it into puzzle pieces, and then only if you have enough puzzle pieces you can recover the value. So say you put all 4 puzzle pieces together, you see what the value is. But if you're below the threshold, say you only have 1 of the puzzle pieces, it's perfectly hiding, you learn nothing. So note that this is better than the puzzle that we know in the classical sense, where even if you have 1 out of 1,000 puzzles, you learn like a color, you learn a shape, maybe not the image. Here it's really perfect, you learn nothing. And in order to decrypt, you have to get together and put the puzzle pieces together. And this alone is not enough, because we also need to be able to process on this encryption. So we need to have a way to generate sums and products of the encrypted values without needing to decrypt in between, and without needing to reveal the secret that they encrypt. And for the sums, you can simply think of summing up puzzle pieces, so the red plus the red and the yellow plus the yellow, if you think of it representing values. And multiplications are a bit more complicated and here require interaction, but you just have to assume that we can do that. And once we have that, the solution is actually very simple. So now, like, this is for a 4-party case. Now every party just takes one of the colors. So we have one party taking the red color, one party taking the yellow color, and so on. Initially, every party has its input that it wants to keep secret, but it wants to input into the computation. So how is this done? So the red party just splits up his input into 4 pieces: red piece, yellow piece, blue piece, green piece, and then just send the corresponding puzzle pieces to the corresponding parties. So keep the red one, send the yellow one to the yellow party, and so on. And note that this does not reveal the input, because each piece on its own is hiding. And next, the parties can recurse through the circuit using the fact that the circuit is just a number of additions and multiplications, and perform each addition, each multiplications on the pieces individually. And finally, once they went through the whole circuit, what they have is the pieces to put together to the output. And this does not reveal anything about the computation, about the intermediate values on the way, so they can just exchange it, put it together, and get y, the output of f, applied to x1 to xn without learning anything more. And so some remarks. There was this what if, for example, I cannot tolerate if I assume there's more than a third of the parties corrupted. So there's also a version as long as you assume an honest majority, and you don't need to assume any, which we typically have to in cryptography, any computation and tractability assumption. So this is secure against even a quantum adversary, unbounded adversary. If you go beyond, if you trust less than half of the parties, then you need to have some extra assumptions, for example, cryptographic assumption, but also there you get post-quantum solutions. So for example, using specialized post-quantum crypto, such as speeds that you will hear more about later, or fully homomorphic encryption, you get efficient post-quantum secure multi-party computation, even if you assume that everyone else except for you behaves dishonestly. So you really only have to trust yourself and no one else. And this has also additional advantages, being more efficient. For example, speeds is much more efficient than these early theoretical results, and fully homomorphic encryption, you have better round complexity, but on the other hand, high concrete overhead. But putting all of this together, the corollary that we get is that if the function f can be computed efficiently, then it can also be computed securely and efficiently, and even post-quantum securely. So in theory, this is all solved. And so what about practice? So there is already, since there's many examples, this is just a few, and you will also see and hear more about this today. So the first large-scale application of MPC was a sugar beet auction in 2008. In Denmark, and since then, a lot has been kicked off, a lot has been happening. And another example was 2014. The Estonian government started MPC project in order to be able to make secure statistic analysis of joint databases, for example, to find out if computer science students work next to their studies, are they more likely to drop out. And as you can also see here on the slides, many of these developments actually include techniques that were co-developed by CWI, like the sugar beet auction, the Helios voting scheme, and also the Estonian application. And and also to remark here that the basic protocol layout is universal, and this also gives rise to an emerging area of secure algorithmics, where you really want to transform an efficient algorithm into concretely efficient MPC solution. And there's many more things already happening and will be happening. So benchmarking between companies that want to keep their company secret, credit rating, fraud detection, threat intelligence analysis, machine learning, many applications there, research data mining, and Also, distributed security, you can think of that you don't trust the microchip of a single provider, but you have microchips from multiple providers emulating a single one. So even if one provider would act malicious, you would still not lose security. And so with all this, can we say, okay, this is all solved? Maybe industry has to step up now. We researchers at least can relax. That's unfortunately not quite the case. So in theory, we have that efficient computer programs imply efficient circuits, but there may be a substantial overhead. And so we have a lot has happened since the 80s, of course. But still, we're not quite there. We don't have this universal compiler that gives us, given an efficient algorithm, a concretely efficient solution. And there is an additional issue that the circuit itself must be oblivious. So, for example, a while loop would leak when you end it. Would leak something about the program. So this is, for example, something that is expensive. So MPC program is still a skillful art, and there's lots of things to do. And if you want to hear more, you will learn more about the practice today. If you will want to learn more about the theory, I refer to the book Secure Multiparty Computation, Secret Sharing. That's the first textbook on secure multiparty computation by Ronald Kramer, Ivan Damgaard, and Jesper Buus-Nielsen. And yeah, with this, I'd like to conclude. We're happy to take questions now or later in the panel. And thank you very much. Enjoy the rest of the day.
Yes, thank you very much, Lisa and Ronald, for this introduction on the fundamentals of multi-party computation. And as a good tradition, you always finish, more research needs to be done, because I first was thinking, well, most puzzles are solved. We only have to apply it to cases, but to use your words, Ronald, there's still enough room for PhDs at Omega in the sky. Can I abbreviate it like that? Okay. Questions from the audience. Jelle Vos. It's a very difficult question. What is, in your opinion, on post-quantum multi-party computation? Is it a must for new protocols, or for now just a plus? Who of you would like to answer this question? Kick off you.
Okay, so I don't think there's a very quick answer to that. It depends on the application. Yeah, so if you have an application where no long-term security for 30 years to come is required, then probably secure multi-party computation, if it relies on, say, computational complexity primitives from cryptography, that are not in the realm of post-quantum cryptography, may be used for a long time to come, actually. So, but that's for only those applications that do not require very long-term security. For those applications that do, say, when secure processing is done on data that's encrypted, and the data that is encrypted is under a regime of long-term security, and it's in the high assurance regime, then we definitely need post-quantum crypto security. One can think of even information theoretic security, which is possible for MPC, but we can also think of using dedicated encryption schemes from the post-quantum crypto regime. And in fact, many of the most practical approaches to secure multi-party computation do use post-quantum crypto primitives. Information theoretic security can be attained, so security against an all-powerful adversary, but there are many advantages to using post-quantum crypto from an efficiency perspective, but also from the perspective of tolerating, very good at tolerating dishonest majority, in fact, N out of N security. So I guess this is a bit of an answer.
So yes, yeah, we're working on it. Anything to add to it, Lisa?
Yeah, I just also wanted to stress that actually it's very different than in the realm of signatures and public key, where post-quantum comes at a price. Often post-quantum is the best you want to do anyway, just for efficiency reason, for secure computation. So kind of a win-win, nice situation we're in.
Okay, thank you. We'll do one more question from Ifke. Have any of these real-world trials for multi-party computation resulted in new theoretical goals or questions that were not in the original theoretical models? For example, new desirable features. Lisa, what is your take on that?
So for the examples I mentioned, I'm not exactly sure what kind of theory. I think it's always the case that it's very good to work together with industry and with practitioners to see what is really the requirements that you kind of need to get, and maybe also what is the cost that you're willing to pay, and also maybe find trade-offs to get the best what is still required. But I think it's I think it's very difficult. Maybe you know of an example.
Yeah, well, let's say new theory that, or theoretical questions that result from practical applications. I guess that, of course, one can think of certain security features that come in handy, maybe verifiable secure computation that turns out to be interesting for very specific applications. But I think that what practical applications most teach us is our notion of complexity of protocols, because in the literature one tends to so make a rough calculation of the resources that are required, but in practice, especially when there's demanding application with a lot of data, with real-time computation, people have to take a much more refined approach to analyzing the complexity of the protocols. So I think that it's in this direction that most advances are attained, and then most of the research, subsequent research, then goes into actually improving the protocols on these parameters that result from a more refined complexity analysis.
Well, it occurred to me that most of the references dated from the 80s, so probably most of the puzzles were solved and the applications came afterwards and didn't change the theory at that point. Yeah,
well, no, the theory has taken a huge flight even since the 80s and 90s. What we've presented here is just the very basics, but especially in the last 15 years, the complexity, the performance of secure multi-party computation has improved dramatically, and that's not just because of programming, that's because of new fundamental ideas that actually allow you to perform multi-party computation much faster. And actually none of these developments we've been able to put into a very short introduction. But again, quite a few of these are described in the book, but there are other interesting, excellent surveys available on the internet that address more recent technique.
Okay. Well, thank you, Ronald and Lisa, for that. Lisa, as you already mentioned, MP speeds or MPSPDZ, what is that? Well, our next speaker will be talking about that. Marcel Keller, all the way from Australia. He works at Ciro's Data 61, and his presentation will be about MP speeds, a versatile framework for multi-party computation. Marcel spent most of his career bridging theory and practice in multi-party computation. He's a senior research scientist at the Commonwealth Scientific and Industrial Research Organisation, Data 61, which is the data and digital specialist arm of Australia's National Science Agency. After completing his PhD at Aarhus University, he spent a few years at the University of Bristol, where he started working on implementation of multi-party computation that eventually would form the basis of MP speeds. It's a framework that covers more than 30 multi-party computation protocols in a variety of security models. MP speeds, it stands for multi-protocol, and all the other letters are just the initials of the inventors of the first protocol, so that's where the name comes from. Marcel, over to you. Well, in the audience at home, if you want to enlarge the slides, you can. Most people already did. And here we have Marcel. Yeah, the background is real. It's not my shirt or anything, but Marcel. Yes, yeah. Okay, please take it away.
Yes. Thank you, Chris. Thank you for the introduction. I want to begin with a short disclaimer that is express my personal views and not the official view of the CSIRO. Okay, so as you have heard in the introduction, the purpose of secure multi-party computation is to compute on data while keeping it secret. And the concept here is to replace a trusted third party. Now, with the actual parties in the actual protocol, there are a few questions to be answered in a so-called security model. which mainly are how many honest parties are there, apart from the fact, of course, how many parties there are overall, and whether dishonest parties follow the protocol or not. And all these options open a space for a variety of protocols. And as Chris has mentioned, MP-Speed supports more than 30 of them. Actually, I have stopped counting at some point. Next slide, please. So if you support this many protocols, you want to ask yourself, well, like what is the high-level view over multi-party computation? Like how can you abstract and unify multi-party computation? So I would like to somewhat further the notion that Ronald has introduced in the introduction, and I would like to call it the black box. I already forgot what term Ronald used, but that was the big omega thing. So basically the view that I like to take is that in multi-party computation, we have this black box that has values inside. And these values are unknown to the parties, but the parties, they have these handles for these values. So they know their values, but they don't know the actual value, of course. And what the parties can do is they can input values into the black box, and they can agree on computing on these values. And then the result of the computation will create a new value in the black box with a new handle. And eventually, at the end of a computation, the parties can agree to output a value, either globally or just to a particular party. And this is the model that we want to capture with a protocol. And it is important to note that this concept applies to any kind of secure computation. And this is why it helps so much in unifying many different protocols. Next slide, please. Another important aspect, which is also something that has shown through in the introduction, is that in a sense, all protocols come with two core operations. One is some sort of addition and the other is some sort of multiplication. And it's almost always the case that the addition works without communication, but the multiplication works with communication. And again, this is a factor that is shared across almost all, I would say, multi-party computations. So again, we can use this to abstract things. Next slide, please. So to make it slightly less abstract and give you an idea of what I mean with this addition, multiplication paradigm, I would like to present this protocol that is called Beaver Multiplication. And essentially assume you have an X and a Y inside the black box. So that's symbolized by the blue boxes here. And we also have the facility to do addition in the black box. And we want to compute the multiplication. So we want to compute a new value that is X times Y securely inside the black box. Next slide, please. So we start by introducing two new values, A and B, and then we just rewrite this X times Y equation a bit. Next slide, please. And what we get is that if we on top have a random A and a random B inside the black box, as well as A times B also inside the black box, we can actually reduce the multiplication to addition, subtraction, and a bit of linear operations in the way that is outlined at the bottom. Essentially what we do, we add the random A to X, we add the random B to Y, which then makes it okay to reveal these values because they're essentially hidden by the fresh randomness in A and B. And of course, once we have revealed them outside the black box, we can do multiplications, whatever we want. And we can also have this public-private multiplication. And then doing that, we can get to x times y inside the black box without actually having the multiplication inside the black box. However, this of course requires that we get this random a times b triple from somewhere. And this is something that is at the heart of the speeds protocol, but I don't really want to go into that in this talk. Yeah, so basically this is just like to give you an idea how this communication could happen. And the communication here happens when we reveal x plus a and y plus b. Next slide, please. So we have established that addition doesn't require communication, but multiplication does, and we have a protocol for multiplication. So what is the implication of this? Well, think of these two simple computations. On the left-hand side, we have a sequential computation. So if you look closely, you'll see that the second line depends on the first line. So we have to compute z first before we can compute u. On the right-hand side, however, all the input values x, y, v, and w are independent of each other. Next slide, please. So with the protocol that we saw before, this means that on the right-hand side, we can do the mask and reveal of x, y, v, and w all at once, doing the computation in the communication in one batch, and then we're done. On the left-hand side, however, we have to do the mask and reveal for x and y first in order to compute z, and only then we can do the mask reveal for z and w. So we have to do this in sequence. And often communication rounds are very expensive. So whenever possible, you want to take the approach on the right-hand side, batching all the communication together. Of course, on the small scale, this is very easy to achieve. You just look at the equations and manually program this, if you will. But imagine on a larger scale. So for a computation that is as large as this, you don't want to do this by hand because it's just too tedious and there is no cutting through all of this and finding out what's going on. And well, this slide is of course just a bunch of random stuff. In a sense, you will often find in a larger computation that that's exactly what you're ending up with, because a lot of operations reduce to a lot of multiplications. So in reality, you will end up with something that looks like this, and you don't want to optimize this manually. And this is something that is essentially at the core of MP speeds, is this automatization, this automized optimization of communication rounds for a given computation, because as we've seen, running as much communication in parallel as possible saves communication rounds, and that can save a lot of time. Next slide, please. So if that was a bit abstract, let's look at the more tangible example. On the left-hand side here, there is a bit of code, as you will find it in MP speeds. There is a matrix of secret integers, and we want to find the maximum of every row in the matrix. The straightforward loop at the bottom essentially just iterates over all the rows, and then for every row iterates over all the columns, and one by one finds the maximum. However, without optimization, this essentially means that we do as many rounds of maximum computation as there are entries in the matrix, roughly the number of rows times the number of columns. However, with the optimization that is available in MP speeds, we parallelize all the row computations because they're all independent of each other. So we can do that. So what is left is that instead of having number of rows times number of columns, rounds of max, we only have roughly number of columns, rounds of max. But this is not even the end yet, because next slide, please. It is actually beneficial to, for every row, instead of like going through the values column by column, we actually would rather have that we compute the maximum as a tree. So we take the first two entries and the third and fourth entry, and we do the maximum of these pairs all in parallel, and then we do another round of pairs in parallel and so on. And that way we can actually reduce the number of maximum computation rounds to the logarithm of the number of columns, which is another big optimization in asymptotic terms. And this just demonstrates the further power of MP speeds, because there's just a simple function to do this, and you don't have to spend any further effort. Next slide, please. So zooming out, how does MP speeds work conceptually? Well, we have seen you can program with Python on the high level, and then this Python high level code is run through a compiler that does the optimization that we just saw. And after the optimization, it outputs a specific bytecode, which is then run in a virtual machine. And I would argue it's absolutely necessary to define a new bytecode that is specific to multi-party computation, because we really want to have a bytecode that allows to parallelize hundreds or thousands of multiplication, and none of the bytecodes that you would come across in other settings, think of Java or the LLVM internal bytecode, gets anywhere to this. So we really want to have something new that is specific to MPC, because MPC is so different to computation on processors. And thanks to the compiler, we can also have a quite extensive library with plenty of functionality, mathematical, fractional. I will talk about this a bit later when we come to an example. And there is an increasing amount of machine learning functionality, because now my work is mainly focused on privacy-preserving machine learning. At the bottom of the diagram with this virtual machine, I should say there's actually more than 30 virtual machines, because there is one for every protocol to make sure that we run as efficiently as possible. So adding a new protocol to the framework doesn't slow down running any other protocol, because we have to figure out at runtime what to do. Next slide, please. So this brings us to the next section on machine learning. How can multi-party computation help with machine learning? Well, a commonly proposed approach is to outsource machine learning in a privacy-preserving manner. So you have entities that hold sensitive data. Think of the hospitals you can see on the left, and they want to train a machine learning model on that data together, but they don't want to give their data away, because it's too sensitive and it might not even be possible legally. But what they could do is outsource this computation to a bunch of independent parties, where it is fair to assume that a number of these parties behaves in an honest way, so doesn't collude with other parties and try to leak any data. So these computing parties on the right, they run this black box together, and inside the black box, they train a machine learning model. And once they have done so, they can either release the model, or they can even keep using the model just inside the black box for what is called inference. So before I go to the concrete application, here's a short primer on deep learning. So deep learning is a popular concept for supervised machine learning. Supervised learning means that we have known input-output combinations. So think of pictures of cats and pictures of dogs. And essentially what we're doing there is we give the computer a lot of pictures of cats, a lot of pictures of dogs, and eventually we want to come up with a model so that the computer can automatically tell us which one is a picture of a dog and a cat. And in deep learning specifically, we model this input-output computation that we want to come up with as a chain of functions, where some of these functions that have parameters that we want to figure out during this process called training when we use the example data. Mathematically, we define a so-called loss function, which is a function quantifying the quality of the parameters. And we want to minimize it because this means a high quality of the model. And the way how the training works is that we use differentiation on the loss function to minimize it. And we use that in an iterative process. And with differentiation and the chain of functions, we can use the chain rule of differentiation. And this whole process is called backward propagation. Next slide, please. So this slide is a rough overview over what components I've implemented in MP Speeds to achieve this secure training. At the very core is a concept called quantization, where we represent a fractional number as an integer by multiplying with the power of 2 and then rounding. And this allows us to reduce fractional computation to integer computation without using fully fledged floating point computation. And the reason why we want to do that is fully fledged floating computation is very or relatively expensive in MP Speeds, generally in MPC compared. But integer computation is much cheaper, and it turns out that machine learning, the quality of the machine learning doesn't degrade too much when we use this computation, this quantization, sorry. So, and at the bottom, you see a number of mathematical functions that we have used, comparison, division, exponentiation, logarithm, and square root. Some of these functions aren't trivial. However, there are algorithms on how to compute these functions that are used on CPUs and in mathematical library. And in MP Speeds, we have implemented more or less the same algorithms, of course, modular quantization, which does degrade the quality a bit, but it turns out not too much. Next slide, please. So now we come to what the actual algorithm, machine learning algorithm and dataset we have used in our implementation, which is this famous MNIST dataset. It consists of tens of thousands of handwritten digits as 28 by 28 grayscale pictures, and the output we want to see is one of the 10 digits. And this has been called the hello world of machine learning. And as far as I know, it was also the first to demonstrate the utility of this so-called convolution, which is a locality-aware linear function, because, of course, in image recognition, like pixels next to each other, they do have a connection that matters. Next slide, please. So we have implemented this famous convolutional neural network by LeCun et al., which is called LeNet. And we also have implemented the so-called AMS-grad optimizer, which I would argue is quite an advanced algorithm for updating the machine learning parameters. There are 4 linear layers in this model. And linear layers means these are the layers that have parameters that are adjusted by the training. So we found that we can run this on some AWS instances in reasonable time, namely that it takes only 9 minutes per epoch. And epoch is essentially one run over the whole data set. And we found that after 1 hour, we have 99% accuracy, which means that we recognize 99% of the digits correctly on a test data set that is separate from the training data set. And you can see in the graph that the accuracy, or the testing error, which is just the inverse of the accuracy, tracks relatively closely to clear text computation. It is not quite the same, and most likely that this is because of the quantization. So we don't attain the same precision. Next slide, please. So this brings us to the final section of my talk, where I want to go on a higher level away from like details and technicalities. And one of these things is that I get asked now and then is that, well, what is suitable for secure computation and what is not? And I think Lisa has mentioned it earlier, that the main differentiator here is called the data-dependent computation path. So what does this mean? Well, let's think about the example of deep learning. And one reason why deep learning is a very interesting application for secure computation is that the computation is very predictable. You know which layers you're going over at which time. And even within the layers, say you have a layer that does matrix multiplication. And in matrix multiplication, you know ahead of time, if you know the sizes of the matrices, you know ahead of time which elements you're going to multiply by which element and what you're going to add up and so on. So it's this predictability that makes a computation suitable for multi-party computation. There is also what I would call small input-output functions, and essentially all mathematical functions. Think of logarithm, exponentiation, square root, cosine, falls under this because there is one number input, one number output, and there is no side information. And this is also an aspect that makes it relatively easy for multi-party computation. On the other hand, we have these issues of data-dependent computation paths, especially notable in graph algorithms, where you are in a specific node and you want to like traverse a graph. So you can only go to another node if there is an edge, but the edge might be privacy relevant data, the existence or non-existence of the edge. Think of a social graph, whether you're friends with someone or not, that might be very sensitive information. But that means that the computation, in a sense, like depends on the data that you would like to keep secure. And then that's much tougher in multi-party computation. And because a common way to do dictionary data structures is a tree, are trees, and trees again are a form of graphs, we essentially have the same problem. Next slide, please. And just before wrapping up, I would like to give a few opinions, also as a setup for the panel to follow. And the first of this is that I would like to see more utility and less mystery in the area. And by that, I mean that it is understandable that people have like a shallow understanding of what's going on with all these black boxes and protocols. But I would argue, if you think of it like in a more modular term, and you take all the progress into account that has been made, it's not that hard anymore. And I want to give an example. So in arithmetic circuit computation, comparisons are not trivial. However, it has been 15 years since the first paper in the area, and many have followed. And yet now and then I come across a paper that sort of seems to imply as if that is a new problem to solve. And that is simply not true. Nonlinear functions, they are not trivial in arithmetic circuit computation, but there's also not that much black magic going on. And MP-Speeds implements a lot of non-linear functions. The next point is that I would like to point out that there are lower bounds. For example, if you want to compute an AND gate, we know that there has to be communication. This, of course, doesn't really set an absolute bottom on the cost of a particular complex computation. And we have seen that there has actually been quite some progress over the last 15, 20 years. Yet, like now and then, I read something along the lines of, oh, look at how much faster everything has gotten. So it will be even more faster in the future. And to that, I would say, well, in investments, past performance doesn't mean future performance. And I think we should be aware of that in multi-party computation as well. And then the last point is directed at people who interact with me about MP-Speeds on GitHub and elsewhere, which I'm of course very happy about. But yeah, thank you for the GitHub link. I'm very happy to interact, but sometimes I feel like I'm getting a bit weird question where I'm wondering, what are people trying to do? And then once I dig a bit deeper, I figure out what people actually wanted to do, and then they somehow failed and they tried something else. And only then they asked the question. So I would just like to ask people to tell me what they want to do, what their intentions are, because that helps me help them, and it also helps to further develop the framework. Whereas if people have overly specific questions, it sometimes seems like people are just trying to poke holes in my software, and that just leaves a bit of a sour taste. Yes, and this brings me to the end of the talk. Can I have the previous slide again, please? I just wanted to go through the links. So as I said, MP-Speeds is on GitHub. There is more than 100 pages worth of technical documentation on this site called Read the Docs. There is an academic paper on IACR ePrint. And last but not least, you can follow me on Twitter. And this concludes my talk. Thank you. And of course, I'm happy to take questions.
Yes, well, thank you very much, Marcel, for your contribution. Yes, there are questions, of course, from the panel, but we'll start with the audience. We got 4 questions, and I'll read them aloud to you in chronological order, and you just pick the one you would like to answer first. Shall we proceed like that?
Yeah, that's fine with me.
Okay, we'll do that. So one question which came, well, already pretty soon in your presentation by Jurjen. Could you please comment on the suppliers of so-called multi-party HSMs, promising to be an alternative to physical HSM boxes? I have a hard time believing their claims, and HSM is probably hardware security models like that. The second question, which came, well, say halfway your presentation, was by Bart. The parallelization problem seems related to register allocation and instruction reordering done by CPUs and compilers. Is there overlap in research between this project and register allocation and instruction regarding reordering? That's a question from Bart. So the third question was by Laurens Veen. Multi-party computation sounds a bit like GPU programming. GPUs don't branch, and they're highly parallel. Is any research being done that explores this analogy, or is it too simplistic? And the last question was also by Bart regarding suitability. Matrix multiplication is suitable. I presume this is mostly for dense matrix. Are there any options for sparse matrices, or is that immediately too data dependent? So which of these 4 questions would you like to answer first?
They're all very interesting.
You can also
questions.
combine them if you like.
I like to. Yeah, I think. Well, okay. The 2 middle ones. There's certainly an overlap there, and the answer there is I'm well aware of the parallels, and I would say what we have done here is certainly inspired by whether systems or CPU research, but then again, it hasn't really led to a intensified collaboration, and I think that might have been because once you dig deeper, the commonalities stop. And I think I tried to allude to that when I said we in MP speeds there's this bytecode and there's no limit to how many multiplications you do in parallel, and this is simply not something that happens in silicon because silicon is finite. So that puts a limit on that, and that kind of changes the cost and whatnot. So I'm not entirely sure how much space for research there is there. But it might also be that I haven't talked to the right people yet. Then we had a question on hardware, on these virtual hardware security modules, and I think that's a very fair application of MP speeds. Absolutely. Of course, I guess you could quibble over the name, on virtual hardware. What is that? But I think you have to give them a bit of slack. That, of course, they want to latch on to a concept that people know, and you can argue that, hardware is the physical black box and MPC is the virtual black box. So it is fair to make this case. And what was the last question again?
That was from Bart. Was regarding suitability. Matrix multiplication is suitable. I presume this is mostly for dense matrix. Are there any options for sparse matrices, or is that immediately too data dependent?
I think there was a paper not too long ago called Zoom something, but I think that might have been published before the whole world went on Zoom. I think with sparse matrices and the algorithms that deal with sparse matrices, you probably run into this data-dependent computation path, but that just because it's not that straightforward doesn't mean there's nothing you can do. I can't. I know there's a paper like at the back of my mind, but I'm not really sure what it actually does. So I think I can't give a conclusive answer there.
Okay, well, perhaps Bart can elaborate on that. Keep using the chat during the panel. Marcel, thank you for computing these multi-party questions. Back to the table, again with Lisa and Ronald, and also Thijs Veugen. Briefly introduced you at the beginning of this day, but let me do the elaborate bio on you, as you are a senior scientist at TNO already for 22 years, and he's a leading scientist on cryptography at TNO. You're also working 1 day a week as a senior researcher at the crypto group of CWI, and before joining CWI, you held similar positions as a part-time senior researcher on applied crypto at Delft University of Technology. And together with Marcel, you formed the program committee of this day. As Marcel already said, his opinion was, well, more utility, less mystery, beware of lower bounds. Please tell me, what was your impression of his presentation, Thijs?
Well, I liked his presentation. What I liked most was the part where he started implementing a neural network with MPC. Because, well, people know MPC because it's very secure. And the price you usually pay is that it's a lot slower than the non-secure version. Neural network is one of the, say, most complicated algorithms you could think of. And by implementing that with MPSPs in a reasonably amount of time, sounds to me like a good accomplishment, showing that even complicated algorithms are possible with MPC.
Is TNO already working with MPSP?
We have looked at it, yeah, but there are other MPC platforms available, and we try to use all of them.
All right.
And see.
All 30 protocols.
Yeah, also the various protocols, yeah, true.
Okay, yeah, so less mystery, yeah, and more utility. Yeah, that's what Marcel called to. Would you agree with that, when you talk about multi-party computation, more utility, less mystery?
Well, I think that Marcel has presented his personal view on this, and I think that was very convincing. I think it's important that practical applications of multi-party computation get well developed, get implemented, get benchmarked, alongside development of more theory that can be applied to this practice. But and I see a very healthy, flourishing international community that is developing all of this. So.
Yes.
Quite hopeful for the future for MPC.
Yeah. And I guess you agree too, Lisa, right?
Yes.
Yes. More applications. And well, we'll see more applications this afternoon, of course. But we're still in the fundamentals. Please elaborate, Lisa. Beware of lower bounds. But what did Marcel mean by that?
So I guess that at least as I understood his point, it was that people maybe sometimes tend to promise too much or say, oh, we have this magic and we can, now it's for free or something like that, which you can never have. You will, of course, always have an overhead. But on the other hand, I think by now we can do a lot of things that were not thought possible. Like MPC for a long time was this cute theoretical experiment that's like nice for researchers to think about.
And for millionaires.
And for millionaires, yeah, that have a lot of time, but not something that you can actually see and that will actually come into practice. So I think it's very exciting, and I think there is a lot of things that we can now do that I don't know, I mean, I'm not in the game for so long, but that I thought much more than was thought possible. But of course, there is limits, theoretical limits that we will always have to pay some price for doing things securely.
Yes, yes. Any comments on the rest of the presentation of Marcel?
For me, it was super interesting. So,
Yeah, I saw you nodding all the time.
Yes,
And
yes.
especially when the complicated formulas came around, I saw Lisa nod. Yeah.
No, I think it's super nice to see these efforts and to see really, to have examples to really see it, make it into practice, and to see, I agree that it's super cool to see it for something like machine learning, and that it can be done, and that like also at very good precision. And see the efforts combined. So yeah, it's very cool. Thank you.
Okay, yeah. So yeah, Marcel, you're pretty cool.
Thank you. I appreciate that.
Yeah. Any comments on that, or shall I go to the audience, because there's more questions from the audience amongst them.
May I?
Yeah, sure. Please do.
So I wanted to add to Ronald. This is actually a one sentence that I had in my script, but forgot to say when I talked about more utility, less mystery. Like, is of course like by any means, don't stop the research. Absolutely. I mean, we want to see more research, and sure, there is 15 years of secure comparison protocols, but a better one might be just around the corner. I think my grievance was more about it seems that not everybody is aware of the literature, and so basically the less you're aware of the literature, the more mysterious everything looks. So absolutely, research, of course. There's no doubt about that.
Oh,
That's what I wanted to add.
Yeah, so by less mystery, you didn't mean that we are mysterious about multi-party computation, but we should be more open and educate about the fundamentals of it.
Yes, very much so.
And read Ronald's book, of course.
Yeah. Absolutely.
Yeah, absolutely. Yeah, okay. Thank you for that. Any comments on that, Ronald?
Well, we agree here. Of course, at some point, wider circles around the cryptographic community get confronted with the possibilities and perhaps also the desirability of MPC. And, people read, they find some survey or a book, and, they start to do it, do it yourself. DIY, but still, programming is at a state where people who know how to program, they can just program maybe anything. But if you're still, as you're playing around with secure multi-party computation, it's still so it's very advanced, but it's still so much under development, practical development, that it requires interaction with people who know the literature and who know what's really going on. And I think that's also perhaps a bit what Marcel is pointing out. You don't want people reinventing the wheel or solving the wrong problem. So, as you see with a lot of technology that moves from fundamental scientific research to practice, there is sort of a stage in the middle where we're not fully in the light, we're not fully in the dark, but that's where there's a lot of interaction between theory and practice. So the theoreticians or the scientists who work on the fundamentals and the people who know the practice, and there needs to be a lot of interaction. And it's also, say, our collaboration from CWI with the people at TNO that often takes precisely that shape.
Is that true, Thijs? I mean, your collaboration, is it mostly that CWI does the fundamentals and TNO does the applications of multi-party computation, or do your researchers also add to the more fundamental academic kinds of notions of multi-party
You see that those things are strengthening each other, because you learn from the fundamentals what's possible. At TNO, we talk to customers, we know what their needs are, we know how you could apply the fundamentals there. But while doing so, you come up with different questions. Like, but the general framework is for doing that, but I want something just a little bit different. And then I go back to the fundamentals. I say, well, we need a new fundamental building block because we need something different.
Yes.
And that goes back and forth, and that makes it very interesting.
Is it speeding up recently? Because the first theoretical notions came from the 80s. We didn't have fast computers and not many data back then. But well, currently we're speeding up with huge data sets, processing at high speed. Does that also challenge multi-party computation at a more fundamental level, or are the fundamentals staying the same?
Of course, it is also what Ronald said earlier. The past decade, there have been fundamental improvements to multi-party computation technology, and especially with regard to the speed. For example, the separation of a pre-processing part and an online part, where you put most of the part in the pre-processing, such that the online phase can be very fast. And for a practical application, that is very helpful. Yeah.
But we do one more question from the audience, Marcel, before we go to the final poll and break. From Martin van Dijk. Does multi-party computation also fit large-scale federated learning, where big data constitutes many thousands or 10,000 local data that should remain private in themselves? That is, each local client does not want to give away the local data that it gathered and uses to compute local updates. Can the amount of communication for multi-party computation in such a large-scale setting be contained?
That's a very good question. There's certainly touch points there, and I would definitely argue that in the machine learning community, what they call federated learning, there with their aggregated updates, you could see that as a special case of a multi-party computation protocol, and there's definitely more research to be done in this area, and sort of like have a dial between multi-party computation and sort of more like very localized federated learning. So yes, but like in the end, doing everything with big data in the black box together with the lower bounds, that might be a tall order, but never say never.
Yeah. Okay, thank you very much, Marcel. So Martin, yes, it can be done, but more research is needed. Well, that's mostly the answer to questions like that. Before we go to the break, let me pop in the last poll question. So what is your opinion now about applying multi-party computation in practice? So we now talked about the fundamentals, and after a break, we will be having several case studies. Could you say, well, I believe it's not useful at all? It might be possible, but many hurdles to take. I can see possibilities or huge opportunities. It's a real game changer, putting multi-party computation in application. I see the stats going up. Nobody is answering not useful at all yet. Well, I guess those people already left the webinar. No, or else you wouldn't join us, of course. Now, I mean, everybody sees huge opportunities because that's why we're here, you know, and especially with the current computer power, putting all these fundamentals in practice, of course. Just a test question. Then again, 14% is saying, well, it might be possible, but many hurdles to take. Those are the academics, of course. They see all sorts of intelligent puzzles to be solved. I can see possibilities. Most of the people say 51%, and huge opportunities, a real game changer. And I guess that percentage is going up after the break when we have our applications, of course. Good. Ronald and Lisa, thank you very much for your contribution, educating us on the fundamentals of multi-party computation. You're off now. After the break, Thijs will return. Also with Mark Abspoel from CWI on HIV research, very fascinating, and Martine van der Gaar with her TNO spin-off Link site. And the poll question will also return after the applications, so you can see what you learned in the meantime. And well, keep using the chat, and we'll see you back after 15 minutes. Bye. Okay, ladies and gentlemen, welcome back at CWI in Business, live from the harbor in Amsterdam and also live from Australia with Marcel Keller, who will also join us in part 2. New at our table here on my left, Mark Upspoel from CWI. He will be talking later on improving HIV treatment choice and multi-party computation. Also new on our table, Martine van der Gaar from Linkside, which is a TNO spin-off company, which we will be talking about. But we continue with Thijs Veuge, which I already introduced before the break. He will be giving you an overview of present and future multi-party computation applications from TNO. And you can join us in the chat, and please do. So, Thijs, take it away.
Thank you, Chris. Well, now we heard what MPC is, what it can do. Now I will lead you through the applications. And you will see that there are many more applications that were mentioned before. First, a couple of trends, which make sure that you know how MPC is well positioned. The first trend is about increasing value creation from data. This is supported by the International Organization for Economic Cooperation and Development. You can create value by sharing data and doing smart things with that. Smart in the sense of AI and machine learning. Also acknowledged by McKinsey and the Dutch AI Coalition. When you want to create value from data, it is essential that you combine data from different sources. For example, during our coronavirus, where we're now in the middle of it, you need to combine tracking data with medical data to give sensible insights into the medical situation. Also acknowledged by Financial Times is that there is much more to be done with medical data. Think, for example, of making personalized medicines by genetic data. But there's much more. Also, the area of anti-money laundering. I will come into that later. The second trend I want to talk about is the more increased attention for privacy. I guess everybody knows the General Data Protection Regulation. So the fines are increasing. Everybody is going more aware of privacy. So treating sensitive data with care is getting important. And not also because of privacy reasons, but also because of commercially competitive reasons. Those two trends create a paradox because people want to share information, they want to collaborate, get new insights, but they are restricted by privacy and confidentiality. In the middle of this paradox is MPC, which is the technical solution for solving this paradox. As I promised, anti-money laundering, why is this such an interesting case? To the left, you see a picture of a professional anti-money laundering organization with lots of different roles, a lot of people. Those people are getting more and more expert in money laundering because you can earn a lot with it. Currently, it's 16 billion euros only in the Netherlands, and it's growing. And what makes it successful for the criminals, it's very hard to detect. Currently, only less than 1% success rate estimated for anti-money laundering. On the other hand, financial institutes have the legal obligation to detect money laundering, and it incurs them large cost to have hire more and more people and investigate more thoroughly this. So there's a huge opportunity. Why is MPC interesting there? Well, you can see that by comparing those two pictures. To the left, you see a transaction network, well, not a network, a transaction of a single bank. The blue bank, which has transactions with the green bank and the red bank, but it cannot see any further transactions like you see in the right picture. In the right picture, you see the combined transaction network of those three banks. And typically, money laundering is not done within one bank, it's done over several banks. So each bank wants to find money laundering. The data is too sensitive to share, but they all want to find money laundering. So that is typically why this is an excellent MPC case. Another case, which is not really a case, but a technique, and I mention it because it's a relatively simple technique, but the impact is huge. So what is secure set intersection? So to the left you have a blue database, to the right you have a green database. Typically they contain persons. Persons have an ID and some other attributes like name, number, street, think of anything. And the goal of secure set intersection is to find the overlapping items. Which people do we have in common? It can be, the question can be, how many people do we have in common? Or which people do we have in common? Or what is the average age of the people we have in common? Can be anything. And that is called secure set intersection. Why is this useful? Well, I mentioned here a couple of examples. The picture on the right is about older people which have already a pension, and sometimes they're allowed to have an extension, an additional pension. But that's only allowed if their income is below a certain threshold. Now, how to find those people? You have the Sociale Verzekeringsbank, which collects all the data about the pension, about the people who are currently having a pension. You have the Uitkeringsorganisatie Werkgeversverzekering, who collects all the data about the incomes. Two different databases cannot be shared together, but you need to bring them together to get those people attracted so that they can enjoy their additional pension if eligible. Second example is between the police and Centrum Indicatiestelling Zorg. The police, they give out weapon permits to people who want to carry a gun. And the CIZ, they register confused people. And not just confused people, but very confused people which by law are not allowed to carry a gun. The police is obliged by law to check whether any person asking for a permit is very confused or not. So that's typically, again, secure set intersection. Third example, FCINet, Financial Crime Investigation. It's an international organization. Each country has its own list of financial suspects which they suspect having done some kind of financial crime in their country. Those countries will not share those lists because that's way too sensitive. But if you know that some person is followed in many more countries, that makes it much more interesting. So you can solve that by secure set intersection. Then you know which people are looked after or are sought in various countries. And the final example, which is maybe not known, but Google already uses MPC. They combine search results with sale results. Everybody knows Google search, and then sometimes at the end you get recommended certain products. You click on the link, and then you go to the company that sells the product. Google cannot see you entering the company and buying the product. So Google will never learn where you actually bought the product. But if Google would know that, they would be able to make very more accurate recommendations for you. So again, two databases, Google with who knows which person clicked on which link, and the company who knows which people bought their products. By secure intersection, you can accomplish that. So this is a bit an overview about current cases. When I look at the future, I see a huge possibility for distributed machine learning in healthcare, because in healthcare you have a lot of data fragmentally stored. You have machine learning coming up, and with that you can derive all kinds of interesting insights. One example will be given by Mark after this talk. Other challenge is combining MPC with other privacy-enhancing technologies, like, for example, differential privacy. As you know, MPC is protecting the computation with sensitive inputs. But the output can still be sensitive. It's not protected by MPC. Differential privacy exactly does that. It protects the output. So by combining MPC and differential privacy, you can make the entire solution more secure. Other interesting combination is MPC and blockchain, which will be elaborated on by Martine later in our talk. And finally, exploitation, because I think that this technology is now ready to be exploited because there are so many opportunities, and I think that the next coming years we will be seeing a lot of that. That was my talk.
Okay, thank you very much, Thijs. There are no questions from the audience yet, but just to get things clear now, that if like governmental business parties go into multi-party computation, you need a third virtual party in order to do the computation. Do they just use an algorithm and they're all set by themselves, or is this third party also a real party needed? And if so, what kind of demands does this play on this third party?
Yeah, so you could say a virtual third party, but in practice there is no third party, because what MPC does is it avoids the same computation as having a third party, which does all the secret things for you. So we don't have a third party, and so we have, I don't know, 2, 3 or more parties doing the secure computations. How do they do that? Well, they need a cryptographic protocol for that. They need software for doing that. Mm-hmm. So at each party there needs to be installed cryptographic software such that the correct computation is done in the right secure manner. That's what you need.
Yeah, so who then checks if the model is correct? One of the involved parties, or do you also need an external party in order to check whether the model works?
Yeah, that is a good question.
Or you call P&O.
That's a good question. So, for example, if you go exploiting this, then I can imagine that certain parties will develop services like, let me check whether the MPC is done correctly at all the parties.
Yes.
But in general, you could say that the computation can only proceed if all the parties agree. Mm. So usually, in beforehand, they all agree on on an algorithm, and each time you could say a party needs to press the go button, and then you can go to the next step.
Yes. Yeah. Okay. We do have a question from the audience. It's Martin van Dijk again. Thank you, Martin. Do you think multi-party computation will be generally applicable? That is, general multi-party computation libraries that can match any kind of application, or is it very specified on the kind of computation you're doing?
Yeah, good question, Martin. Well, in theory, every application, in theory, everything is possible, but usually what you run into is execution time and communication. So it depends a lot on the application, on the amount of data that you need to process, the complexity of the algorithm, the time within it has to finish. So in theory, yes, but in practice, there are all kind of hurdles to take.
You always need adjustment for each case. Yeah. I have a question from Hans Janssen. Is there already any form of standardization available or in the making? I assume Hans missed the first part of this webinar because MP Speed is that, right? Or did I get it wrong?
No, MPC is a platform which you can do generic computations. Mm. But with standardization, it's like the NIST standardization for post-quantum cryptography.
Yes.
Yeah. But I know there are standards in the making, but they are very preliminary.
Okay.
Yeah. So, for example, in ISO, there are people thinking of how to standardize multi-party computation in certain settings.
Okay.
But there are no finished standards yet.
So, Hans, there's work to be done, and maybe you can be the celebrity setting the ISO standard for multi-party computation. That would be cool. Okay, let's go to the next speaker. So, Thijs, if you could hand him the clicker. Mark Upspool, also from CWI, on improving HIV treatment choice with multi-party computation. It's a project of CWI, but also together with University of Amsterdam and Philips, the Dutch electronics company. Mark has is a PhD student at CWI at the Medical Institute at the Leiden University since January 2017. Under the supervision of Ronald Kramer, you saw in the first part here, your research focuses on secure multi-party computation, both in theoretical foundations and applications in secure algorithmics. Among others, Mark has published several articles that broaden the scope of multi-party computation, from evaluating circuits over fields to more general communicative rings. Before joining CWI, he also worked as a data architect at Current and as a technical consultant at Orange Valley. You already started programming work since you were in high school, so you're pretty skilled on that. Mark Absoel on improving HIV treatment choice, and you can join us on the chat, please.
Yes, thank you, Chris. The project, I'm going to talk to you now about work we did in the context of a project with TNO, the Institute of Advanced Studies at the UVA, and Philips Research. And this was a TKI project, which is sort of a Dutch subsidy vehicle for private-public collaboration. It was a one-year project. It was about, we started halfway through 2017. And the goal of the project was to develop new, or sort of investigate whether we could apply MPC techniques to practical use cases. So in the project, we identified two use cases in the medical domain. One of them was from the UVA and the other one was from Philips Research. For both of them, we developed a solution using MPC with a proof of concept implementation. So I'm going to talk to you now about the use case from the University of Amsterdam, which is about choosing optimal treatment for for HIV patients. So this is a difficult problem because there's not a single virus. There's many different mutations of this virus, and also the virus mutates throughout the lifetime. Also, the virus mutates more the longer the treatment progresses, and if the treatment is bad, then the virus will mutate more, leading to treatment failure, and also increased drug resistance and a faster progression to AIDS. So it's very important to choose optimal treatment, but because there's so many different variables and mutations, this is a hard problem. So currently, doctors, they take these decisions for treatment. They only have about 5 minutes per patient, so it's a very time-constrained environment. And they base their decisions on current medical research, their knowledge, and their experience. And to assist doctors with these tasks, the UVA developed what they call the comparative drug ranking system, where the doctor inputs sort of a patient's mutations, and then the system gives for each of the treatment combinations, or each of the treatments, which is sort of a combination of different drugs, they give the expected resistance. And these resistances are always based on sort of rule sets triggered by specific mutations. This system consults 3 different rule sets. These are updated every year by an academic committee based on current research. They each have different areas that they focus on, I guess. But we asked ourselves the questions for this use case. Every time a patient needs new treatment, I mean, we can have a new patient, but at some point this treatment will fail. So hopefully it's a long time. It can be after 10 years or so. But a patient comes back. And then we get a data point. We get feedback on the prior treatment, which is the time it took for this treatment to fail. And so we asked ourselves the question, can we use this data? Can we sort of augment this system instead of just searching for, based on existing rule sets and existing research? Can we sort of use this as a data source? There's 2 problems. The first problem is that doctors don't want to publish their decisions for reasons of liability. For example, it might be found out that one doctor always prescribes suboptimal treatment, and then they might get sued, and they don't want this. And the second problem is that a patient's HIV genotype is actually privacy sensitive. Of course, it's not their own DNA, but the patient's HIV genotype might reveal something about who infected them or whom they might have infected. So this is sensitive material. But so we see we have some privacy restrictions, but we figured we can solve this using MPC. So what this computation looks like, or the function sort of that we want to compute, is that, say, every doctor keeps a local record of all of the treatments that they have prescribed to patients and the results. So these data points, the time it took for this treatment to fail, given a patient's genotype. Then suppose a patient comes in, maybe it's a new patient, maybe it's a recurring patient, then they submit this patient's HIV genotype into the system, and then all of the doctors also submit their treatment results. And then the computation will output what's the average time it took for this per treatment, it took for the treatment to fail, what's the average time it took for the treatment to fail. That's what the system wants to compute. So rather than doing this, because this computation needs to be run every time, and rather for the doctors inputting their data every time, we make a secret shared database, basically, or an encrypted database, where each record in the database is this genotype, the treatment prescribed, and the time it took for the treatment to fail. This genotype gets encoded as some vector in some finite alphabet, and then we say that two genotypes are similar if the vectors only differ in a small number of positions. And then we want to compute the average time it took for the treatments to fail. Now, it's important for the computation that this computation, we need to check basically against every row, because we cannot just do searches on this secret shared database depending on the data, because then the access pattern would reveal something about the data. So this is sort of like a fundamental thing in MPC, that every time that you compute on data, you can never, you cannot do branching. You always need to check against every data point, and then you can have these, you operate on these encrypted values that you know nothing about. So in this case, our computation scales linearly in both the size of the data set, capital N, the length of these genotype vectors, and the number of treatments. Now, for our implementation, we set these parameters to be 100 different treatments, 200 different mutations encoded as a binary vector. But this is because it's easier to compute with. And we only look at the relevant mutations. Of course, this viral genome is very big, but research has demonstrated that only a few of these positions are actually important for determining whether a drug has resistance or not, or whether the virus has resistance against a drug or not. And we looked at the number of rows up to 20,000, which is roughly the number of HIV patients in the Netherlands. We implemented this in the Bristol Speeds framework, which is a predecessor of Marcel's MP Speeds framework, and also Skill Mamba, which is a different fork by the Leuven University. And we used two parties connected through a local network. We used the low gear protocol. So this was halfway through 2017. In the meantime, there have been a lot of improvements also in these frameworks, also in the protocols. In our case, for the maximum number that we illustrate here, we can see in the graph, I mean, it's a straight line. It's as I said, it's a linear, it scales linearly. And the maximum time it took for this computation was 24 minutes. Now, this is only the online phase. There's also additional pre-processing to be done. And ideally, this would fit within the 5 minutes that the doctor has, but perhaps with some organizational fixes, this can be improved. So in the project, we have some takeaways. And the first takeaway is that we spent a lot of time on identifying a good use case. You have this tool. I mean, we knew we wanted to do something with MPC, but you have this tool, and the question is, how do you use it optimally? Like, where are its strengths? So initially we thought, okay, maybe because currently the system was that the doctor inputs this mutation string to the system, and then the server at the UVA actually searches this data set. So we thought, okay, maybe we can have this doctor do this sort of encrypt this or secret share this mutation string, and then we can do this search in MPC. But actually, you don't need MPC for this, because you can just do the computation on the client. But then UVA says, okay, but hospitals, they have old machines and they don't get frequent updates and they might be slow. So, but these are not challenges that MPC directly addresses. This is an automation issue. Yeah, this tool MPC, it's basically mostly useful when you have a mutual privacy requirement. So you have two different parties or more different parties, at least two, that have some privacy requirements against each other. We saw that this system that we propose, it's actually something new. You cannot do it otherwise. I mean, there's privacy issues that inhibit you from doing this in another way. So we actually can do something new. And also, we found that the performance of MPC can already be good enough for practical applications, which is a nice takeaway, I guess. Of course, this was, as I said, in 2017. Since then, there have been improvements. So I expect these 24 minutes, it might actually fit within the 5 minutes now. And that is my talk. Are there any questions?
Yes, there are two questions. Thank you very much, Mark. The first question is actually quite short, so you can give a short answer. How many different genotypes are there, roughly?
I have no idea.
No idea. Okay. You can look that on the internet. Just Google on genotypes HIV. Bart, you register time to failure. But if a treatment is really good, it will take a long time to fail. Does that mean that treatments that are more successful might be underrepresented in your database of treatments? A very interesting question. Yeah.
Yes, yeah, of course. I mean, you can modify the system so that it actually adds like a dummy data point or some rough estimate based on the current treatment that has been prescribed to the patient, and just an estimate based on the time to fill. That could be the case.
Yes. So the short answer is yes. I was wondering myself that you mostly approach it from a privacy standpoint. Yeah. Of course, very logical with HIV research. But are there also other advantages to it? So, for example, if you have different pharmaceutical companies who don't want to share their intellectual property or their research findings, can work on a similar data set without knowing what the others are working for. And another advantage I could think of is sharing computer power. So are those two advantages you can add to this platform, or is it mostly the privacy of the patient?
I mean, sharing computer power is not really the case, because MPC is generally much more expensive than just running a computation locally. And actually, as you add more parties, the computation will become more costly.
Yes.
However, so initially we also considered maybe looking at drug-to-drug interactions. And this is a very nice application of MPC, but we didn't find a good, clear way to approach this, basically, because it's a very complicated topic. Mm-hmm. But that I would really like to see this happen in the future, where different pharmaceutical companies that don't want to share their formulas, they can sort of like compute what the interaction of their drugs can be without revealing anything.
Okay. But more research needs to be done on that, right? Yeah. Okay, very well. Martin van Dijk, yeah, you're really going. Since the database is small, can you imagine an isolated compute node or HSM approach that would be a good alternative? And HSM is hardware
security module.
Yes, that one.
Yes, well, I mean, of course, the computation is. I mean, we have this generic blueprint of a computation, and you can also run it on a hardware security module. I guess they give you different guarantees. In this case, we like that there are already different parties. So I mean, using MPC seems natural. But if you trust the hardware security module instead of MPC, then that could also work.
Okay. Well, the audience is really getting loose now, so we'll do one more if you don't mind.
Sure.
Laurens Veen. can't you just run an algorithm once for each combination of virus genome or genome cluster and treatment, and then publish those results? You wouldn't have to run it for each patient that way.
Yes, well, in this case, the problem is that there are a lot of, I mean, we want to search against patients that have a similar viral genome. So it's not really, there is a central, I mean, cluster is not really well defined. So that complicates this approach.
Yes, yes, okay. Yes, so I assume Martina, Thijs, and also Marcia have questions too, but save now for the panel discussion later on, as we will now continue with the next presentation. Yes, thank you. Martina van der Gaar, Linksite. It's a TNO spin-off which provides a software platform for privacy-friendly, decentralized data analysis based on, of course, secure multi-party computation, but also on blockchain technology. Martina is co-founder of Linksite. She has more than 15 years of experience in IT, mostly management functions, with a focus on data science and decentralized methods. She worked at retail, transport, energy companies, and at Capgemini. She joined TNO in 2017 and founded Linksite, well, just half a year ago, but became a spin-off this summer. And Martina will elaborate on Linksite and join us in the chat.
Yes, thank you, Chris. Today in my presentation, I'm going to give you some practical pointers. You won't see any mathematics formulas from me. I will just give you some hand-on stuff that you can work on while using MPC in your business. First, let me tell you what Linksite is about. We believe in creating data-driven insights together without sharing the sensitive data. We as Linksite want to enable you as business partners to do those analysis yourself. For that, of course, we use MPC, but not just MPC. We also are a huge fan of thinking about governance, because we believe that you need governance to set the conditions for doing your analysis. And I will explain with a few examples. The first, I think some of you already know that example, but imagine that you are with a group of friends, for example, and you want to know the average income. And you want to know, are you on the good side or maybe earn less than your friends? So you use MPC to calculate your average income. You get a result, but then one friend leaves the room, and then you redo that calculation again. And then you learn something from both of the outcomes. You learn something about the salary income of that fourth person that left the room. And that is a situation that if you do statistical analysis with MPC, that's something that you would like to prevent from happening. So MPC itself is not enough. You need to think about the conditions under which circumstances you can do those analyses. In practice, that means, for instance, that you have to think about how large should be your population in your analysis. If the number is 1, you learn something specific about that one person. So you want to set that condition to maybe 20, 50, depending on the size of your total population. Another example would be that if you're doing small deviations in your analysis, you get also information on really small subgroups that also is revealing something about that group, maybe too much for you to know. So you have to think about what conditions are needed. Another example is thinking back about calculating the average income with your friends. What if your data set changes over time? What if a person is added to the data population? What if someone is leaving? You don't want to redo the analysis because you will learn something again about that part of the population that has changed. So governance is really needed as an addition to MPC. And we within Linksite use that by combining MPC with blockchain. The blockchain there help us to technically force upon those governance rules. And there's another benefit to using the blockchain. The blockchain helps us in creating an audit log, and therefore it helps you as a company to be compliant as well to several rules and laws. That is for Linksite. Today I'm going to share some of the learnings on a project that we ended the first half of this year. Here you see your picture with all our happy faces with the partners that we did the project with. In May this year, we were the first in the Netherlands to apply MPC on real patient data with 4 parties. And like I said, we learned quite a few things that I want to share with you. First of all, no real data means no real learning. If you're not using any real data, while trying MPC, you're not going to tick all those boxes. Let me explain. If you're doing legal and you're not using any real data, what kind of discussions would you have with your data protection officer? Probably complete different ones if you were using real data. Same goes for security. Would security really care if you were on a test environment? Because everybody knows on a test environment apply different security rules than if you were on a production environment. So again, no real data, no real learning. Also for business owners, they want to do the analysis. But what would they really learn from the value of MPC if it wasn't for using real data? And on that topic for business owners, since we're here today with TNO as well, what we also learned in this project, that you should have, if we're going to expand MPC and use it on large data sets and even more businesses, you should also think about how should those, how will we make sure that we're talking about the same data? That's also something you only learn when working with real data. And therefore you also need to think about ontologies. So looking at my former colleague on my left, to Thijs, I hope that also Tien is going to do research on combining MPC with ontologies. Back to no real data, no real learning. Same goes for data subjects. It is their data. How would you know how to approach them? Would you know whether you need an opt-out or need any kind of consent? How would you know if you're not using any real data? So what we did, we used real data. Legally, we had we hired some top guns to explain from a legal standpoint what it is that our tooling need to fit looking at GDPR or other applicable laws. From a security standpoint, we hired an external company to do some extensive penetration testing on our system. So also that we knew from that angle that our system was safe to use. Well, the business owners, they could do the analysis themselves. And for data subjects, we learned, at least in our case, in that specific case, we were able to use an opt-out for the patient data. And we know already that in other cases, we have to use informed or even explicit consent. So if you want that learning experience, you need to use real data. And there's one that is very important, one more learning, I want to make explicit. We have to be able to explain multi-party computation at different levels. Today we have seen multi-party computation has been explained like you can see on the screen. It has been explained by using formulas. It's called CWI in business. But I can assure you there's no business person that understands this. No legal counselor, no data protection officer in your company, no data owner understand these formulas. They have a complete other background. Think about the case, everybody has signed a form of formal contract. And you know those contracts are written in completely different language than we see here on the screen. So you have to be able to translate what is happening from a technical standpoint in their own language. And that's also why we hired those external legal counselors to help us really explain step by step what it is, what the system does, how it works, so that the legal counselors can make up their own conclusions based on that. And I'll give you one more example about the people it concerned, the patients in this case. Because believe me, they are really concerned what is happening with their data, especially when somebody else is using their data. They are really engaged in knowing what is going on and how it is protected. And I'm And we have to be able to explain it to them as well. And they have different backgrounds, lower educated, higher educated. They have more technique backgrounds or not. And they all should be able to understand it. And we really had the experience that there were people so much involved that they would come to the hospital, whose patients it were. And they really came to the hospital banging on doors. During the lockdown, they were banging on doors, shouting words, names, the person who was under the letter, but words that I cannot repeat it, but it shows how much engaged they are and how much they really want to understand. So on this topic, I think for everybody who's here today, we really have to make steps in this area that everybody understands it. Well, I hope that even after the whole talk, not only my talk, but for the whole day, I hope you guys are still enthusiastic and see the possibilities. Oh, the slides are not working. Yes, thank you for the support. I hope you all are still enthusiastic and see the possibilities there are with MPC, because that's what we as Linkside do, where we enable that power. And I hope that you all are interested in taking those next steps, and we as Linkside can help you go through all the steps, go through all the loops that need to be that you need to take to get that real learning experience yourself. Thank you.
Well, thank you, Martine, for this presentation. Especially the last part really struck me, because this whole morning I've been thinking, well, it can be correct from a mathematical point of view, but it's about real people, this data. And what if these persons start asking, you know, what's in, what kind of personal data for me is in there, or a legal counselor says, well, is it legally proven? You can't just show the formula. You need a lot of explanation to do. So thanks very much for elaborating on that. Yes, we do have some questions from the audience. Thank you for that. And I'll just do them in chronological order. Jurien asks, considering that blockchain is a multi-party protocol by itself, can't you just include the functionality in your multi-party computation?
No, I don't think so.
No,
I rely on my technical colleagues who have a way more better background in this. I think no, but really,
yeah,
if you want to know the details.
So the question was about blockchain, or?
If you can use the functionality that is in MPC, whether you can use that.
To circumvent blockchain.
Yeah, you combine that in the blockchain.
You can incorporate this functionality that blockchain provides into an MPC computation.
But the question actually starts with, considering that blockchain is a multi-party protocol by itself, is it?
Yep.
Yeah.
It is, okay. Can't you just include the functionality in your multi-party computation? Yes or no?
I don't think so.
No, don't think so. No, we don't think so, Jurgen. Thank you for the question. Yeah, you're right with that, Thijs? You're hesitating, right?
It has been integrated already. So the question is, are we now looking at a blockchain system or an MPC system?
It's actually
well,
both.
it is an MPC system, and the blockchain is supportive. And one of the reasons I would really say no is because if you're using the MPC functionality in the blockchain itself, you would store data on the blockchain. And that's at least something from a Linkside perspective that we really would like to prevent.
Yeah, don't share data. That's the whole idea about multi-party computation, or secure multi-party computation, of course. Okay, here we have Martin van Dijk again. We see main momentum towards a data exchange and sharing economy with, well, for example, Gaia X. You'll know that project, right?
Yep.
Cloud European. As European initiative where data is stored together with policy tags. Do you think your technology fits such environment? Well, it will be a great business model to have.
Again, I don't have a technology background, so this question is not really fit for my knowledge.
Perhaps Thijs can answer.
Yeah, well, in theory, it's very interesting to have MPC on top of Gaia X or any other data sharing platform. Then you can use the data sharing functionality already there, and put an MPC layer on it so that you can securely compute with your data. So in theory, I would say it's a great functionality.
Yes, of course. Adding secure multi-party computation to GAIX sounds self-evident, but should that be using Linksite? Just say yes.
Yes.
Yes, use Linksite. It will be the best platform to do this, right? Okay. Next question. Benny. We didn't have a question from Benny yet. Thank you for your question. What was the medical context of the case in which you applied multi-party computation to real patient data? Which medical problem did it solve? Yeah, you briefly touched upon it, but what kind of case was this? Or is it
was
still...
really brief. We used multi-party computation to see what happens if patients are using, with a more chronic disease, use an e-health app. What happens with the healthcare, not only in the hospital, but also what happens at the first line? Think about the general practitioner, what happens with the pharmacist. How does using an e-health app, what consequences does it have for other parties giving care to that patient? So that was the case.
Yeah, okay. Francine, thank you very much for this justified intervention. And I think she mentioned what you said about explaining, but according to her, it's not just about lawyers and patients understanding, oh, no, the question goes away, understanding the technology, but also about the developers understanding the non-functional requirements coming from legal and moral considerations. Yeah, do you see that in practice? I mean, GDPR already touched upon it, but there's many other legal obligations you need to meet in order to process sensitive data. How do you explain it to the developers? How do you encode law?
Yeah, well, how do you do? Yeah, the same way as we did. That's the first conversation. We used the top guns that were able to understand both worlds, as well as the legal side as the technical side. So you could say they were sort of intermediate, helping. And of course, we explained to our own developers again as well. So yeah, you need some communication to understand both worlds, and you should be also willing to, of course, want to understand it.
Yes. Yeah. Well, actually, Mark, I can consider you as more on the developer side, working on very sensitive data. So, are you being approached by legal folks and managers, demanding that your models meet their needs? And how do you communicate from the other side?
I mean, I'm not doing any development currently.
Yeah.
I'm just doing academic research. So,
but you need to explain to other people how the model works, right?
Yeah, of course. I mean, a part of an academic is communicating to people outside of academia what's going on. Mm-hmm. Yeah, I mean, you can explain stuff on many different levels. So I was part of a research project from the Horizon 2020 project called SODA for 3 years with Philips Research and the University of Aarhus, the Alexandra Institute, and also the University of Göttingen, which had a legal department. So we had a lot of discussions. They had some legal experts, and we had a lot of discussions, and especially in the beginning, a big task was explaining to them what MPC actually is. And you see they constantly make, you say one thing and then they sort of like go in some direction which that you don't want, basically. It's a very hard thing for people to grasp. And I think I saw this in this project.
So then you show the formula and you say it's true, and then they start, well, okay, but with your model, would it be possible to, well, and then they come up with all sorts of ideas don't work, but you still need to convince them, right?
Yeah, you don't use formulas. You just explain the concepts, and then yeah, you go into you enter a dialogue with them and see what they understand, and then you sort of like do fine tuning, and in the end, people will understand it.
Yeah, yeah. Well, Thijs, well, you also need to deal with this. So the examples you mentioned were mostly about fraud investigation. Well, there's a whole bunch of laws there. It's a lot of sensitive data, and it's all about a whole lot of money, billions. Yeah. So how do you facilitate the communication vice versa? So from, let's say, the people who are more on the societal side towards the developers, and from the developers to them. How do you facilitate this communication?
Yeah, in general, you just need a lot of communication. That's the more basically it. And for example, talking to lawyers is generally very difficult for a technical person, and the other way around. They kind of live in their own worlds. So it's very important to try to understand their world and try to explain such that it fits into their world. Yeah. That's more or less the challenge. Yes. And yeah.
Okay. I have some other public remarks on your presentation, but let's first go to Marcel Keller again, all the way from Australia, who has been watching. Marcel, we've been presenting 3 application cases: healthcare, HIV, spin-off side, financial fraud, stuff like that. Well, you're more from the fundamental side with your models. How do these 3 presentations struck you? Any comments on them?
Yes. So I have to say, I guess, well, I'm familiar with Mark's work, so I have heard about that one before. Whereas, like the last presentation, that was more novel to me, and I'm well aware of the challenges, like talking to non-technical people, and this is like very much indeed where I appreciate work being done, but as you said, that like I'm not very involved there, so I'm somewhere in between, maybe. Like I'm not an entirely theoretical researcher working at the university, so from university perspective, I'm more hands-on and lots of programming. But of course, at the same time, I'm not working with lawyers. So from that perspective, I'm definitely more technical. So yeah, I found the last talk very inspiring. That, of course, like not to say that the other talks weren't good, but they were like more familiar territory for me, I would say.
Yes, yes. Yeah, you're pretty much at the core of the developers, but there might be other developers more at the side who need to communicate with others. So yeah, this is what we've been doing now, communicating cases to the broader audience, both the fundamental as well as the application side. So let's throw in another poll on what people learned in the meanwhile, because our first poll was already, what is your opinion about applying multi-party computation in practice? And we'll now ask the same question again, see if any of the opinions changed. So, my mouse is going the other direction. Yeah. So again, what is your opinion about applying multi-party computation in practice? Not useful at all, might be possible, but many hurdles to take. I can see possibilities, or huge opportunities, real game changer. Well, I'm quite happy to see that nobody opts for A, not useful at all, because then this webinar will be worthless. Yeah, nobody dares to. Or it might also be the other way around, that people had high expectations, and because your cases show the real effort that needs to be taken, some people might be negative in the end. So it doesn't judge the quality of the presentations, but rather the level of reality which we brought to our viewers. So in the meantime, there's 20% saying it might be possible, but many hurdles to take, of course. 35% says I can see possibilities. And the largest percenter is now going into the direction of huge opportunities, real game changer. Let me see if I can go back to the results of the previous, what they said. Yes, actually, it went up. So a lot of people went from might be possible, and I can see possibilities, to huge opportunities. So yes, we actually convinced some of the people in the audience, both the people here as well as Marcel, to actually get to work with secure multi-party computation. Yeah, so how do these figures impress you guys?
Well, I think it's a good cause. Yeah, definitely. Like I said, NPC can really be of value, not only in helping to do stuff in a maybe an easier and a more GDPR compliant, more private, secure way. But I also think that if you go behind that step, you will see that the technique will also give you new opportunities for other businesses or business models, etc. So, yeah.
Would you agree?
Yeah, I think that, well, as one of the takeaways I mentioned in my presentation, I think that the MPC actually enables new solutions, and that's why I think it's very exciting.
Yes.
So yeah, I see a lot of stuff, a lot of potential for the technology.
Okay. So Thijs, if you would summarize the advantages, so the privacy friendliness is a no-brainer, of course.
Mm-hmm.
We also touched upon that you can share, well, data which can be sensitive from an intellectual property standpoint. What other advantages can people see in secure multi-party computation in general?
So yeah, in general, it's a technique of putting data together which you have never dreamt of before getting them together. Because you never thought of them getting together because too privacy, too sensitive. Think of any reason. When I talk to people who do not know MPC, and I explain them, and then usually I know a bit about their business, so I give an example in their world, and then I say, oh, is that something you can do? Oh, but then I know this and this and this and this. Which might also be very fruitful to me. So you see that when the ball starts rolling, many more opportunities come up. Mm-hmm. So when people start fantasizing about which sensitive data can I share if there wouldn't be no borders, mm-hmm. then you open up new worlds.
Okay. Marcel, did we forget any of the advantages we can have with multi-party computation?
Not that I can think of.
Okay,
I mean, to be honest, like from the more groundwork perspective, I think one thinks mostly about privacy.
Yes,
and that's of course like the main point, and of course in like intellectual property, but that's not really part of my day-to-day thinking.
Okay, well let's then briefly continue on the privacy aspect of it. Let's turn it around. Let's say we have this very valuable data, say on healthcare or finance, and we want to de-anonymize the data. So if a patient pops up or a criminal pops up or any other individual or an individual who wants to ask, what kind of data are you all storing on me? If you want to have the opportunity to de-anonymize data, is that something you need to build in advance, or can you recalculate who the actual person is, what the data is about?
So usually in MPC setting, data can be recovered as long as all the parties collude, or they put their data together again on the table, like making a third party again.
Right, so you need all the parties to agree on releasing the data on a single subject, and then you can redo the calculation again and say, okay, with this person we had that data and combine it. Right, so everybody needs to agree. So if there's one party saying, no, I'm not participating, then you miss pieces of the puzzle.
That's why each party can control whether they're going to release data on a certain person or not.
Yes, yes.
I mean, this exact number of parties that can sort of abstain, that also depends on your specific system.
Mm-hmm.
But it could be that it's okay if one party refuses to cooperate, and you still have enough parties left that if they cooperate, then they can reveal the data.
Okay. Does that also count for checking whether the model is correct? So take your research, a certain genotype with certain treatment is very efficient, very effective. And there is a patient with this genotype and treatment, but it doesn't work. Mm-hmm. So, well, then they say, well, the model doesn't work. There's flaws in there. Can you then also say with all the parties collaborating, okay, let's de-anonymize this part so we can check whether the model works or not?
I mean that
the model is correct.
I mean, of course, you could investigate if the source data is available, or anyway you have this, or all parties agree to reconstitute the original data. Then yes, you could do this. Of course, whether a model is correct, you can also sort of test this, just giving a description of the model. Mm-hmm. But yes.
Okay. So, Thijs, if we go to the financial fraud cases, imagine, well, we have these banks and a governmental party saying, okay, well, we are going to put this data together, and if there's a suspect in there, something pops up, and we can de-anonymize this suspect, and we can go there. Imagine there's a fourth party, a real party, a law enforcement party, saying, well, I would like to have this data because, well, we're looking for terrorists, or they show up with some sort of law saying, well, we can actually use this data. Does it then also count that all the other parties involved need to agree on that?
Still, yeah, we're entering a dangerous area here.
Yeah.
But yeah, in principle, it's the same. So it depends also a bit how you design the system. But as long as a threshold number of parties agree, you can reveal it, and otherwise you cannot.
Yeah. Yeah.
That's the technical explanation.
Yeah, I was just trying to get the optimism a bit down to be more realistic, and because everybody was looking, well, very huge opportunities. But then again, we touched upon several hurdles which might need to be overtaken: legal approval, efficiency, whether it's already accepted or not, how you communicate about it. So let's throw in another poll, the final poll for you, the audience, to check what do you think is the most important aspect for applying MPC in practice. So that's what kind of hurdles need to be overtaken before we can really use this method. It's mostly legal approval. And again, we need to communicate to the people, but it might also be legally impossible because the law requires certain things to it. Is it more efficient performance? As you said, well, it burns a lot of CPU doing this, and every part you add to it becomes more complicated. Is that C, mature solutions? Well, we saw some solutions here. Some are in design phase, but most of them are already applied, which will count for your case. Societal awareness and acceptance. Well, imagine, being a patient, saying, well, your data is being used to see certain patterns, and they might say, well, I won't like you to use it because it will get on the street. I see data leaks all the time, and again, communication is key. Or other, and if you have other hurdles you thought of, just put them in the chat, and I will read them aloud. Yeah, I think the legal approval, we talked about that, but very few people think that that's one of the main hurdles to take. 10%. Efficient performance, 27. Yes, we have complicated models, need to work on that, but yeah, we can solve that. Mature solutions, that's the hurdle is getting most votes, 41%. And well, that's why we have this webinar, of course. There are already solutions, but we're trying to get them more mature. And the societal awareness and acceptance, 14%. Two is other. It's 9%, so 2 people. If you think other, put them in the chat and can read them aloud. And if not, we'll keep it to that. Okay. So, ladies and gentlemen, in this Monday morning, from we started at 10 o'clock here in Amsterdam time, 8 o'clock in Australia time. Marcel, it's now 11 o'clock at night?
Actually, it was not. It was at 6 p.m. and now it's coming up to 8:45.
Okay, okay. Well, please take a beer. We'll wait for that. We'll be having lunch, but it has been an honor having you with us. And
Will do.
great you stayed with
Thank
us
you.
all time. So let's give an applause to Marcel. Yay!
Yes.
All the way over there. And let me also thank my guests here at the table and your audience there. So what's next? CWI in business. It's a biannual event we're having. The last was 2019, so the next will be in 2023. Well, who knows what the situation will be there. We will just be standing here with drinks and Marcel will be here. We don't know, or we'll be having a webinar again. Yes, Marcel says. But before CWI in business will be there in 2 years, next year we'll be having a large symposium on secure multi-party computation organized by CW and TNO. The program will be known in between time. And also on the 3rd of November, we'll be having another webinar, again, CWI with TNO, on post-quantum cryptography from the same studio here, and the program will soon be presented to you. Well, let me finish off with thanking Crowdale here in Amsterdam for hosting us, Danielle Colery and Susanne van Dam from CWI who organized, Aaron van Baarsen and Sergio Fer, who've been sitting at home and doing the moderation of the chat. And of course, thank you very much, people, for posing your questions. And sorry we couldn't deal with all of them because we had a tight schedule. And also finally thank Ronald Kramer and Thijs Vegeruur for being our program committee. My name is Chris van der Toff and I hope to see you back again on the 3rd of November with Post Quantum Crypto. See you then. Ciao.